Hello everyone, we will be presenting a project titled Designing a Microstrip Antenna with Defected Ground Structure. Microstrip patch antennas are popular in wireless communication due to their compact size, low profile and ease of fabrication. However, they commonly face challenges such as narrow bandwidth, low gain and reduced efficiency. To overcome these limitations, a technique called defected ground structure is used. Defected ground structure modifies the ground plane to enhance performance by improving parameters like bandwidth and radiation efficiency. The main objective of this project is to design and simulate a microstrip patch antenna operating at 2.4 GHz incorporating to boost overall performance for practical applications such as Wi-Fi and IoT.
Here are the main steps taken in designing the antenna. First, we selected the operating frequency of 2.4 GHz. Second, we calculate the antenna dimension using transmission line mode to estimate the patch width and length. Third, we choose FR4 as the substrate. Fourth, we model the antenna in CST Micro Studio, including the patch, ground and feed line. Fifth, we introduce a defect ground structure below the patch and feed line to enhance the impedance matching. Finally, we simulate and optimize key performance parameters like S11, bandwidth and gain to ensure the antenna works effectively.
Next, I will briefly present the antenna design. We use rectangular patch antenna design for the 2.4 GHz ISM band. We use FR4 as the substrate due to its low cost and availability. The substrate size is 76 by 59 mm with a height of 1.5 mm. The patch itself is 38 by 29.5 mm and made of copper with 0.035 mm thickness. We also apply an inset feed with 0.74 mm width and 9 mm depth to help with impedance matching. Next, the antenna consists of 3 layers. First is top, which is copper patch. Second, the middle, FR4 substrate with 1.5 mm thickness and permittivity 4.4. Last is bottom, which is copper ground plane. And this structure is simple, cost-friendly and suitable for Wi-Fi or Bluetooth devices. And lastly, here's the CST model showing the front and back views. The front shows the patch with the inside pit, while the back is the full ground plane. This simulation helps check performance before the fabrication.
So this is the fabrication process where we start by selecting the FR4 as substrate. Then the antenna is designing using CST Studio. The design then is exported to AutoCAD for PCB fabrication. Next, photolithography and etching form the antenna pattern on the copper. And SMA connector is soldered at the feed point. Finally, we test the antenna using a VNA to measure S11 and VSWR.
To design a microstrip patch antenna operating at 2.4 GHz, we start by assuming the dielectric constant is 4.4 for an FR4 substrate and the substrate height is 1.5 mm. First, we calculate the patch width using the given formula, which result is approximately 38.01 mm. Next, we calculate the effective permittivity to account for fringing effects and it comes out to be around 4.097. Then, using effective permittivity, we calculate the extension length, which is about 0.72 mm. Finally, we calculate the actual path length using the speed of light formula adjusted for the electric effect, subtracting twist the extension length. The resulting patch length is approximately 29.5 mm. These dimensions ensure that the antenna resonates correctly at 2.4 GHz.
For the simulation result for S11 parameter graph, we can see 3 main points. First, the antenna shows excellent return loss at 2.3667 GHz with an S11 value of -41 dB. This means the antenna has very strong impedance matching and very little signal is reflected back. Second, the small frequency shift from 2.4 GHz is still within the ISM band, so the antenna is still suitable for application like Wi-Fi and IoT without any major issue. Third, the use of a defect ground structure or DGS help improve performance. It fine-tunes the impedance, reduce unwanted surface wave, and make the antenna more efficient overall. This is the maximum gain graph, where first is the peak at 2.4 GHz is the highest efficiency, negative 10 dB. Second, efficiency drop below negative 20 dB at 1 to 1.8 GHz. Third is it is suitable for 2.4 GHz application such as Wi-Fi and Bluetooth. Lastly is this graph help to assess how much input power is effectively radiated. A higher dB value means better gain and lower power loss.
Now, let's look at the result and analysis of our antenna design. Specifically, focusing on the VSWR or voltage standing wave ratio. As shown in the graph, the minimum VSWR achieved is 1.08 at 2.3667 GHz. This value is very close to 1, which is indicate excellent impedance matching, meaning minimal signal reflection at this frequency. Additionally, the VSWR remains below 2 across a wide frequency range, from around 2.3 to 2.45 GHz. This is a strong indicator of good bandwidth performance, allowing the antenna to operate effectively across the 2.4 GHz ISM band. This frequency range is commonly used for LAN and Bluetooth applications, so the result confirms that our antenna is well tuned for practical use in wireless communication system. Next, we will look at the antenna 3D far field radiation pattern to understand its performance in terms of directionality and efficiency. The antenna is a high directivity of 6.9 dBi, which is mean radiate energy effectively in specific direction. This is ideal for focused wireless communication, where the signal strength need to be concentrated rather than spread out in all directions. In terms of efficiency, the antenna has a radiation efficiency of 68%. This indicates that a significant proportion of the input power is successfully radiated as electromagnetic wave with minimal loss. Additionally, the radiation pattern is nearly spherical, which provides good signal coverage in multiple directions. This is benefit for ensure reliable connectivity regardless of the antenna orientation. In conclusion, this project has changed our understanding of antenna parameter and simulation tools. We successfully designed a 2.4 GHz microstrip patch antenna with a defected ground structure, DGS. Through simulation, we identify areas for performance improvement and gain valuable hands-on experience using CST Studio Suite. While the antenna performed well, there is still room for improvement through better impedance matching and material tuning.